Hello there, and welcome to BIO100 Laboratory. Today's laboratory is on the metric system, and this is going to be a pretty easy lab for some of you, in particular if you've ever had the experience of using the metric system, maybe having lived in a country where the metric system is used. This won't be any challenge to you at all. However, if you're like a great number of United States citizens, you've grown up with the English system of measurements, measuring things in feet and inches and pounds and ounces and temperature in degrees Fahrenheit. And maybe to you, the metric system might seem like some sort of Eurocentric conspiracy, but it's really not. It's a better system. The metric system is way, way better. I think anybody who's thought about it, even if you're ingrained with the English system of measurements, you have to recognize there are substantial advantages to using the metric system. And it's also the lingua franca of scientific studies. So scientists from all over the world have got to speak to each other using the same figures. And if one person is reporting units in feet and yards and stone, and everybody else is using kilograms and meters, there's a lot of difficulties. All right, so since this is a science class, we will be talking in terms of the metric system, and it's a good idea for you to know what these units of measurements are and how they're used. Okay, so our itinerary, our agenda today is actually pretty simple. We introduce you to the metric system generally, powers of 10, that sort of thing. And then we talk about 3, 4 different kinds of measurements that we might be making: length, mass, or weight, if you like, volume, and temperature. All right, so we're going to start off with just a discussion of the metric system and how it works. I'm going to switch over to this other sheet. Okay, so with the metric system, we're always going to be dealing with a power of 10. And there's always going to be some kind of prefix plus the actual unit. And so our first unit of measurement is going to be a meter. So if our meter is something that's about 39.3 inches, it's basically a little more than a yard. The prefix, what comes before the word meter, is going to be something. It's actually, there are only 3 prefixes that we'll be thinking about, maybe 4 in this class. One is going to be kilo. Kilo means 1,000 times, and so a kilometer or a kilometer is going to equal 1,000 meters. Okay. About 6/10 of a mile, if you like that. So if you've ever run a road race, you know that road races come in 5K, 10K. Those Ks are kilometers, and 5K race is roughly 3.1 miles. Okay. And so yeah, if you're measuring distances between here and Fresno, you would probably measure that in kilometers. Anything that you would normally using the English system of measurements use miles for, you would measure that in kilometers. But it's not going to be a very good unit of measurement for measuring things like the size of a lot, of residential lot, right? Unless you're dealing with a very, very large residence, you probably wouldn't be measuring the size of a lot in square miles. You would probably be measuring them in square feet. And similarly, square kilometers would not be a good measurement. So if we just get rid of the kilo there, we would basically be looking at a meter. And so things would be measured in meters if they're roughly, like the distance from here to the end of the block, or how far away from your car you had to walk in order to get to the classroom. Okay, so that would be sort of thing you'd measure in meters. Now there are other metric prefixes, and one that's particularly useful is centi, which basically means 1/100th. So a centimeter is just 1/100th of a meter. And it would be, it's more or less what we use to substitute for things that we typically measure in inches. Okay, so if you wanted to measure the span of your hand, you wouldn't do that in yards, you wouldn't do that in feet, you would probably do that in inches. And similarly, you'd want to use centimeters as the appropriate unit of length to measure something of that scale. Okay? So centimeters is a really useful thing. We'll be measuring, for example, the length and the width of our work tables or workspaces using centimeters, as well as meters. We'll be doing conversions. The next unit of measurement is going to be milli. This means 1/1000th. And so a thousandth of a meter would basically be maybe about the width of a dime. Okay, and yeah, if you're following along, if you've got reasonably good sense of numbers, you would note that a millimeter is 1/10th of a centimeter. So yes, it's absolutely true that 1 centimeter is equal to 10 millimeters, and this is our next unit of measurement. Right, so millimeters are one example of a unit of length. I guess the only other one that I think is worthwhile mentioning, I think the other unit of measurement, the other prefix we want to talk about here is micro. Micrometer is 1/1,000,000th of a meter. So micro as the prefix always means 1/1,000,000. And if you're doing your math, you'll realize that there are 1,000 micrometers in 1 millimeter. Okay, and so yeah, micrometers are useful for when we measure things under the microscope. If you want to measure the diameter of a typical bacterium like E. coli, you would do that in micrometers. Okay? Or the diameter of one of your epithelial cells that we'll be looking at later on in the semester. A micrometer would be an appropriate unit of measurement, not millimeters, it's too big, not centimeters, too big. Okay, so basically we use these prefixes to create new units of measurements that would be useful to measure things that are of the scale of whatever it is we're measuring. And the nice thing about these diverse units, micrometers, millimeters, centimeters, meters, kilometers, is that they all scale based on powers of 10, which is something that we don't have in the case of the English system of measurements. You might note that there are 12 inches in a foot, 3 feet in a yard, 5,180 feet in a mile. These numbers are kind of arbitrary. They're not easy to convert one from another. So in other words, if you had to convert between feet and miles, it would be a pretty substantial calculation. However, if you're measuring things in meters, the conversion between meters and kilometers is actually pretty easy. Okay, so if you are, if the Olympics are on as I'm doing this, as you're thinking about 100 meters, 100-meter swim is 2 lengths of an Olympic-sized pool. How many kilometers is that? Well, that's actually pretty easy. What you do is you say, well, 1 meter is 1/1000th of a kilometer. So basically, you can do this. You could say there are, it was 1 kilometer. 1 km is the same as 1,000 meters. And basically when we do like a conversion factor, a fraction like this, where we have 1 kilometer on the top, 1,000 meters on the bottom, they're the same thing. 1,000 meters is 1 kilometer. And if you remember back from your math class, if you have the numerator and the denominator that are exactly the same thing, it's 1. And so this is the same thing as multiplying by 1. So in order to get from meters to kilometers, we could use a conversion factor like this and say, okay, well, let's do this. If we multiply this out, if we multiply 100 meters by this conversion factor, this fraction, well, the meters cancel out. We have meters here, meters there, they cancel out. And when we multiply across the top, we end up with 100 over 1,000 kilometers is the unit that we're left with. And so this is basically the same as 1/10th of a kilometer. You could probably have done that in your head. I know. It wasn't a difficult calculation, but basically the steps that you were doing in your head as you're figuring out that, yeah, 100 meters is exactly the same as 1/10 of a kilometer. You were actually doing a conversion like this in your head. Okay? Or if you weren't doing it in your head, now you know how to do a simple conversion. Okay? And so the math is a whole lot easier if we're interconverting between metric units. It's a whole lot more difficult if you're interconverting between English units, right? It'd be the same thing. It's like saying, okay, well, 100 yards. 100 yards is how many miles? It would not be an easy calculation at all. All right. So let's look at a couple of other units of measurement. Another unit, we use a unit of gram for mass. Mass, by the way, is kind of the same thing as weight, but it's not really the same thing. Okay, and there might be a little bit of confusion here because we talk about the gram as being the basic unit for mass in the metric system, to which we use kilos for kilograms, milligrams, centigrams, micrograms. Those are all useful units of measurement. Okay, but the question is, well, what's the difference between mass and weight? Okay, because you're already used to the idea of, well, you're weighing things out. How much does it weigh? You're kind of doing the same thing as determining how much mass, how much matter is there. And one of the constants, one of the rules of the natural universe is that matter doesn't really change in the amount of substance that's there. I mean, if you have 55 kilograms of mass, that's the kilograms of mass of your body. You might say that you weigh 55 kilograms, but the truth is that weight is something that's kind of subjective to the amount of gravity. We can talk about mass and weight and use them interchangeably here on the surface of the Earth because the force of gravity is approximately the same. However, if you were to go, for example, to the surface of the moon and you would weigh yourself, you would weigh a whole lot less, right? The weight decreases with the force of gravity, but the overall matter that you contain, that's going to remain the same. There's a difference between two different devices that we use to measure weight versus measuring mass. And so you might be familiar with with this thing called a scale. A spring-loaded scale, something you might be using to measure the weight of a fish. So you catch a fish and it's got this scale thing, and basically the more the fish weighs, the stronger the force of gravity. It pulls the spring downward, and a little marker drops it down by a certain amount to tell you how much the fish weighs. Now, if you were to take that same fish and move it to the surface of Jupiter, okay, Jupiter is a much more massive planet, so the fish is going to weigh a whole lot more on Jupiter. It's going to be pulling the things almost way down to the bottom. Or if you were to weigh that fish on the surface of the moon, where gravity is weaker, there's less force of gravity, it would weigh a whole lot less. But no matter what, the fish remains the same. The amount of mass is going to be constant. And so we can use mass and weight kind of interchangeably as long as we're talking about measurements that are made on the surface of the Earth, because they're pretty much the same. But it's at the same time, it's a good idea for you to understand the difference. If you want to measure mass, you really want to use something called a balance. Okay, so in a balance, it's kind of like you've got this lever, it's like this thing. Okay, maybe it's like this thing where you've got two hooks. Okay, and you're going to be measuring you'll put your fish over here, and you'll put exactly the same amount of they'll take like a brass weight and put it on the other side, and at a certain level these two things are going to balance. You're going to say, well, the mass of the fish is exactly equal to the mass of this weight that I have on the other side of the balance. And that's going to be the same whether you're on the surface of the Earth or the surface of Jupiter or the surface of the moon or anywhere you go, because the force of gravity is going to be operating the same on both sides of the balance. Okay, so you could say, well, the fish is going to weigh different amounts depending on how strong gravity is. Or you could say, well, the fish is going to have the same mass irrespective of where you are in the universe. Okay. So there you have the differences between weight and mass. And similarly to what we were talking about before, we can talk about a kilogram, and we'll be using some symbols. Kg is kilogram, or kilo, that's about 2.2 pounds. So you'd probably measure your own body weight in kilograms. You could measure the weight of a spoon in grams. You could talk about milligrams. We don't use centigrams too much. Milligrams would be kind of like the amount of drugs there are in a tablet of Tylenol. Tylenol might have 325 milligrams of acetaminophen in each tablet. Okay, so mg is the symbol for milligrams. We can talk about micrograms. That would be, we would use a different symbol. We would basically use the Greek letter mu. G, that's another one that you'll probably hear about, microgram quantities of this or that. Okay. Now, there's one, and for those of you who have lived in other countries where they use the metric system of measurements, a useful measurement, a useful unit is going to be the hectogram. You can say, well, what the heck is a hectogram? Well, it's a gram with another prefix, a prefix we haven't used before, and hecto is going to be 100 times. Okay. So 100 grams is a hectogram. You do the math and you figure out, well, 10 hectograms is 1 kilogram. And so if you're at the store in France and you want to buy a small portion of French cheese, you would ask for French cheese, you would just ask for cheese. Now, you probably wouldn't want to get a whole kilogram. That would be like a deadly quantity of cholesterol for your arteries. You would probably want to measure that out in hectograms. So you would ask for maybe 2 hectograms of your best brie. All right. And so there are other units that go along with the other powers of 10. We're just kind of focusing on the ones that we tend to use in our laboratory: kilo, milli, centi, and micro. Okay. The next unit of measurement for us is going to be the liter. And with liters, we are going to be using a symbol, either capital L or a script L. Okay. And so in our laboratory, we'll be thinking about liters. A liter, for reference's sake, is about the same as a quart. It might be a little bit more than a quart. Okay. So if a liter is about a quart, a milliliter, or ml, is what? Yeah, 1/1000th of a liter. And so, yeah, we'll be measuring small volumes of liquid out today in milliliters. And that's an important unit of measurement. The other units of measurement, like centiliters and kiloliters, are not really used. Now, one unit that is used is a deciliter. Not so much in science, but basically in they're more everyday applications where deciliters might be used. For example, and you might be measuring the volume of Coca-Cola in a typical can, an 8-ounce can. You might be measuring that out in deciliters. Okay? Or if you're in Europe and you decide to pull up to a pub in Düsseldorf and ask for a pour of their best alt beer, it would be coming in a fixed number of deciliters, depending on which pub you're going to. Okay, so yeah, again, there are different. A deci, by the way, is 1/10 of a liter. Okay, so that's going to be our unit of measurement. That's going to be pretty much the instruction that you need in our measurement of liters. Now, as you're measuring liters out, we'll be using a device called a graduated cylinder. which is basically a cylinder with gradations, with little hash marks along the side. And you measure the volume of liquid that's in the graduated cylinder by basically holding this level and making sure that your eye is parallel with this so you don't get any of that parallax effect. And one of the things that I'm supposed to mention to you here, this is actually pretty important, is that when you measure things, if you actually look at the inside curvature of a liquid, you'll notice that it actually curves upward. There's a little bit of a curvature, and that's called the meniscus. Yeah, there's a part of your knee that's called the meniscus as well. Okay, and it's basically a curved lens. And I guess the thing the instruction that I need to provide you is that when you're reading a graduated cylinder, you always look to line things up at the bottom of the meniscus. Okay, so I guess the question is, well, do I read this from the top of the meniscus where it touches the glass, or do I read this at the bottom of the meniscus where it is where that curvature is at its lowest point? The answer is always read from the bottom of the meniscus. Okay, that's if you don't do that, then then you're measuring things out incorrectly. If you need to do a 1 deciliter pour, because you're a bartender in Germany, you would end up pouring less than 1 deciliter if you measured from the top of the meniscus. And no, they don't actually use a graduated cylinder to measure beer in Germany, but if they did, you'd be running that risk. Okay. So before we get to the next unit of measurement, we ought to think about one more thing, because now we've got two different ideas. One being mass, and another being volume. Okay. Mass we measure in grams. Volume we measure in liters. Now, there's another concept that is really useful for us. It's going to be density. And density is equal to an object's mass divided by its volume. Mass over volume. And so you could take an object, you could measure its mass, and then you measure its volume. And we'll be thinking about how to do that. You'll follow the instructions in your lab book for how to do that. And if you take something that weighs a certain amount, you can measure the mass in grams and divide that by its volume. That's an easy way to measure density. And the reason this is important is that you can use density to evaluate whether something is going to be likely to float or not in a liquid. And so if you take water, which is something that we probably would be using if we wanted to float something to determine its density, or to test whether our density calculation is correct. Water has a density of exactly equal to 1 gram per 1 ml. Okay, so 1 gram of water is actually going to be 1 ml of volume. 1 ml of water is going to be exactly equal to 1 gram of mass. Okay? And that's really useful, because if you have something that is less dense than 1 gram per ml, it's going to float. If you have something that's more dense than 1 gram per ml, it's going to sink. And so the float test is a good thing. So if you take wood, for example, wood, if you measure 5 ml, which is the same thing as 1 cubic centimeter. Okay, that's 1 cube. That is exactly 1 centimeter on the side. So basically, if that's a centimeter, 1 cubic centimeter is going to be the same. Cubic centimeter is the same as 1 ml. Okay. Sometimes we also use cc's for cubic centimeter. So if you've ever heard a doctor order 1.5 cc's of this, or that as an injection. That would be the same as the same number of mLs. Okay. So if 5 cubic centimeters of wood is going to weigh 5.8 grams, is it going to sink or is it going to float? Well, I hope you said it's going to sink, because 5.8 grams divided by 5 mLs is going to be a number that's greater than 1. And so it's going to sink. And yeah, there are some woods that have densities that are greater than water. There's some woods that sink. Teak sinks, ironwood sinks, and that's because they have densities that are greater than that of water. Okay, the last unit of measurement that we'll be talking about today is temperature, which is kind of a neat thing. It's a neat concept, because temperature, well, you could ask, well, what does it actually measure? You'd say, well, how hot it is. But how do you know something is hot? Well, you touch it, you feel it, you use a thermometer. What is actually being measured in temperature? Well, temperature turns out to be kind of a neat physics lesson, because temperature actually measures the average kinetic energy. That's the particles of whatever it is that you're touching are moving around, and how much energy there is in the movement of the particles is going to determine whether something is relatively warmer or cooler. And maybe that's a lesson we'll get into later on, but you're probably used to thinking of things in terms of degrees Fahrenheit. And Fahrenheit is this completely antiquated system of measurements where everything is just completely arbitrary. Water freezes at 32 degrees Fahrenheit. Water boils at 212. The human body is roughly 98.6 degrees Fahrenheit. And so we've got these numbers that are pretty good references that are all over the place. And we're going to replace that with degrees centigrade, which is also sometimes referred to as the Celsius scale. Celsius and centigrade basically mean the same thing. Celsius is the person that invented it. Centigrade refers to the fact that you take the temperature, you take 0 degrees centigrade, which is the freezing point of water. H2O freezes. It's kind of like a good reference point. And you take 100 degrees Celsius, which is the point at which water boils. Okay, and you know that the difference between there's a big difference between the freezing point of water and the boiling point of water, but you divide that in 100 individual units, basically 100 little spaces. You make 100 divisions. Each one of those divisions is going to be 1 degree centigrade. Okay? And so that's a very useful way of measuring things. And you could say, well, the Fahrenheit schedule says, 0 degrees Celsius is the same as 32 degrees Fahrenheit. 100 degrees Celsius is equal to 212 degrees Fahrenheit. And how did we ever come up with these goofy numbers? And there's a really ridiculous historical story to that. And I'm not even going to tell it to you because it's so dumb. But yeah, I mean, centigrade and Celsius are much more useful. The only thing that we have to get used to here is, what does it mean? How warm is the room that you're sitting in? Okay, your typical comfortable room temperature room, roughly 70 degrees Fahrenheit, translates to be around 20 degrees Celsius. Okay? So room temperature is 20 degrees Celsius. Body temperature, roughly 98.6 degrees Fahrenheit, is going to be roughly the same as 37.4. Okay. And so if it's 35 degrees outside, it's a really warm summer day. Okay? If it's 15 degrees outside, it's a cool fall day, but it's not freezing yet, right? And that's because we're talking about degrees Celsius. Okay? And so those are the 4 units of measurements. We'll be learning also about how to do conversions in laboratory, but I think I've provided you with enough instruction at this point where we'll be able to save some time in the laboratory. We'll be able to jump directly into our laboratory exercises, and the further instruction that I provide in the laboratory is going to be relatively minimal.